Hey guys, it's Ricardo here, and today we're going to go through a quick review of Le Chatelier's principle. So, first of all, just going to go over the definition of Le Chatelier's principle, and that is if a stress is put upon a system in equilibrium, the equilibrium will shift so as to counteract the effects of the stressor. Now, the way I like to visualize this is I like to think of equilibrium as a scale. And so, we have a scale that's in equilibrium with the reactants on one side and the products on the other side. Now let's say we add a stressor to the system, which we'll go over in a bit, but let's say we increase the concentration of the products. Now the system has to counteract this stressor of increased concentration of the products by rebalancing the scale over on this side and sort of decreasing the products and increasing the concentration of the reactants in order to get back into a state of equilibrium. So now we're going to go through some examples of what can cause these shifts. And so one such shift can be the resultant of a change in concentration of reactants or products. Now, the equilibrium constant K for a reaction, let's say A plus B is in equilibrium with C plus D, can be expressed as the concentration of C times the concentration of D over the concentration of A times concentration of D. So, if, for example, we increase the concentration of C, that's going to put a stressor on this side of the reaction. Now, K is constant by definition, and so if we're increasing C, in order to get back to the constant K, we either have to decrease C or D or increase A or D in order to shift that ratio back to what it was before. Alternatively, if let's say we choose A this time and we decrease the concentration of A, that's going to make the sort of ratio here bigger than K. And so in order to readjust, then we're going to have to either increase A and increase B, or sort of decrease C rather, decrease D. I've just realized I've written that as a D, so I'll just fix that as a B. Next, going into pressure and volume. So another stressor that can be applied to the system is changing the pressure and changing the volume. Now, pressure equals force per unit area. And so if we're increasing pressure, it means we're sort of putting more particles per unit area. And another way of representing this would be to decrease the volume. So an increase in pressure will be proportionate to a decrease in volume, and vice versa, an increase in volume will be proportionate to a decrease in pressure. So let's say we have a reaction now, A plus 2B is in equilibrium with, let's say, a compound C, and we increase the pressure. Now, what the equilibrium is going to do is going to shift to the side with the fewer amount of moles of gas. And so if we increase the pressure, obviously here we have 3 moles, 1 plus 2, and here we have 1. The equilibrium is going to favor the side with only 1 mole, and it's going to shift to the right here. Similarly, the same thing would occur if we decrease the volume, as by decreasing the volume we would be increasing the pressure. But let's say now we sort of decrease the pressure or increase the volume. If we decrease the pressure, the reaction is going to favor the side with more moles, as there's sort of more space within the system. Now, the way I like to visualize this, I like to think of, let's say, a balloon. Now, in this balloon, we've got all these sort of particles of gas running around and colliding. Now, if we increase the pressure or make the balloon smaller, these collisions are going to be occurring far more frequently. And so these collisions here, the reactants here are going to be colliding within themselves and actually forming sort of product C. While if we have a really large balloon, there's going to be a lot less collisions relatively speaking, and so the sort of reactants will be able to exist without forming the product C. So endo and exothermic reactions. Now, endo and exothermic reactions. So an endothermic reaction is one that absorbs heat from its surrounding, while an exothermic one is one that gives off heat to its surroundings. So exothermic is normally denoted by a negative delta H, exo, while an endothermic reaction is normally denoted by a positive delta H. So negative and positive. Now, the way I like to think about this in order to get it sort of straight out every time I come across a reaction is I like to actually include heat in the reaction formula. So if I have A plus B is going to, let's say, C again. C, and I'm told that it's exothermic. Now if it's exothermic, it's giving off heat to the surroundings, so the heat is going to be a product. While if it's endothermic, let's say for a different reaction, Z plus Y is in equilibrium with X, the heat is actually going to be part of the reactants. And so now, if we apply Le Chatelier's principle again, let's say we increase the heat on an exothermic reaction, you can sort of almost view it like you're increasing a concentration of sort of one of the products here, and that's going to shift it back to the left. Similarly, if you decrease the heat here, it's going to shift to the right. Now for an endothermic reaction, so the inverse is true. If I'm going to increase the heat, it's going to shift to the right, decrease, shift it to the left. Just to recap, giving off heat is exothermic, heat in the sort of reactants is endothermic. Now, so we've got our first review question. Here we have methane reacting with oxygen in order to give carbon dioxide and water. So what's going to happen if A, we decrease the concentration of oxygen, or B, we increase the concentration of methane? Now, I'm just going to let you guys pause it if you want to give it a shot. We'll work through it in a second. Alright, so decreasing the concentration of oxygen, so we're going to tip the scale out of balance. So we're going to end up with sort of less sort of reactants than there are products, and it's going to be tipped out of balance. So in order to push that scale back down, we're going to have to increase the concentrations of methane and oxygen and decrease the concentration of carbon dioxide and water. In other words, the equilibrium is going to shift to the left. So it's going to shift to the left. Meanwhile, if we increase the concentration of methane, we're sort of tipping the scale the other way. And so in order to counterbalance it, we're going to have to put in more products, and in order to do that, the reaction is going to have to shift to the right and produce more carbon dioxide and water and have less methane and oxygen. Okay, next up we have 2 potassium dioxide reacting with water, and that's in equilibrium with 2 potassium hydroxide and 1.5 oxygen, and it's delta H negative. Alright, and so what happens if A, we decrease the temperature, B, increase the pressure, or C, increase the volume? So just give you a second to pause that if you want to go through it. Alright, well the first thing to note is if the delta H is negative, we have an exothermic reaction. Now what this means is heat is being given off as a product. So if we decrease the concentration of heat, it's going to tip the scale out of whack, and so it's going to be like that. We're going to need to shift the equilibrium to the right in order to put more pressure back on the scale and get it back in equilibrium. So that answer is going to shift to the right. Next, increase pressure. Alright, well we know that if we increase the pressure, the reaction is going to shift to whichever side has fewer moles. So now let's just take a look at this reaction. On this side we have 3 moles, 2 and 1. And this side we have 3.5, 2 and 1.5. Okay. So, obviously here the reactant side has the fewer moles, so increasing the pressure is going to shift it to the left in order to restore that balance. So we also know that an increase of pressure is proportional to a decrease in volume. So if we have an increase of volume, it's going to be the same as decreasing the pressure. which means right here that it's going to go to the side with the more moles, and so it's going to go to the right. Now, here we have a bit of an interesting one, so I'll just give you guys a second to pause that if you want to go through it yourself. Alright, so here we have reactants A plus B in equilibrium with products C and D. What's going to happen if we add heat? Now, we haven't been given a delta H value directly, but we have been given a reaction profile. And so here we have sort of the reactants, and so we have the energy level of the reactants. Here we have the uphill process, and then it goes down, and we have the energy of the products. Now, the products, as you can see, are at a higher energy level. And so delta H is actually the value between the lines. And delta H here would be positive because it's products minus reactants. With the product being a larger number and reactants being smaller, it's going to equal a positive value. So positive delta H means endothermic, which means heat is going to be on the reactant side. So if we add heat, sort of increasing the concentration of this reactant, which is going to tip the scale like that, and we want to put more on this side to balance it out, so it's going to shift to the right. Alright, so now we have another slightly different question. Just give you a chance to pause that if you want. Alright, so here we have a chain of equilibriums. So we've got A and B, which is an equilibrium of C, then C and D, which is equilibrium E and F, and E, F, and G, which is an equilibrium of H. What's going to happen if we decrease the concentration of H? Now this is just the exact same principle applies. If we're just looking at this one reaction here, just take it one reaction at a time. If we decrease the concentration of H, we're sort of imbalancing the scale, so it's going to be like this, because there's going to be more reactants or less products than there should be respect to equilibrium. And so in order to restore the balance, it's going to shift to the right. So if this one's shifting to the right, that means we're going to have less E and F. If we've got less E and F, the same result's going to happen here, and so this one's going to shift to the right, and the same process repeats here. So this one, A and B, is going to shift to the right to give more C. So ultimately, decreasing H is going to decrease concentrations of A and B, respectively. Now, I think this is the final question. So this one requires some knowledge, external knowledge from the video as well. And so here we have gas, evaporated water, gaseous water, equilibrium with liquid water. And so what's going to happen if we add heat? Now, just let you guys think about that for a second. Alright, so gas going to liquid is process of condensation. Condensation. Now obviously the question's asking about heat. We've got to figure out whether the reaction is endo or exothermic. Now, the way I like to think about it, gas is very, very high energy. It's higher energy than liquid, right? The particles moving way faster and colliding way more. Now, for it to go from gas to liquid, it's got to go from a higher energy state to a lower energy state, right? So that means it's actually got to give off energy because it's going to a lower energy state. And so in order to give off energy, that means the heat is going to be given off in the products. And so it's an exothermic reaction. So if we add heat, it's the same as increasing the concentration of the products here, which is going to tip the scale like so. And then in order to restore the balance, we're going to want to sort of increase this side or decrease this side and shift the equilibrium to the left. Now, oh, nope, we've got one more question. So this is more of a theoretical based question. It's sort of testing your understanding of the equilibrium constant. So I'll give you a second to look at those options and choose. Alright, so what will cause KEQ to change? Pressure, concentration, volume, temperature, or all the above. Now, the important thing to remember of the equilibrium constant is that it's only dependent on temperature. Now, this is very important. A few examples, they sort of assess you on that. And so they might give you, let's say, A plus B, equilibrium with C. Now, increasing the concentration of A, what effect does that have on the equilibrium constant? And what lots of students will do is they'll start figuring out that, okay, we have, this is so it's equal to this, and A, B, okay, increasing A, which is going to make K smaller, so K becomes smaller. That is wrong, very wrong. The only thing that'll cause the equilibrium constant to change is a change in temperature. And so, yep, so that sort of wraps it up, guys. So thank you very much for going through this tutorial. If you want me to cover something else, let me know in the comments down below. And if you have sort of any suggestions and ways to improve the videos, I'd love to hear it. All right, thanks, guys, and happy studying.